This is part 9 of a series on generative adversarial networks. In this video, we will look at the second part of Wasserstein GAN. This video was produced in Korean and translated into English. My voice is generated by AI, text-to-speech. In the last video, we looked at why Wasserstein distance is necessary for efficient GAN training, and also looked at how to find the Wasserstein distance. In this video, we will look at how to apply Wasserstein distance to GAN networks, and also look at how to implement a WGAN model. To understand the WGAN algorithm, we first need to understand Kantorovich-Rubinstein duality and Lipschitz function. Now let's look at the Wasserstein distance and the Kantorovich-Rubinstein duality with a very simple example. We have two discrete distributions PR and PG as follows. I and J are bins of PR and PG respectively. Both PR and PG have only two bins. We want to measure the Wasserstein distance between the two distributions. As we did in the last video, let's make several plans to move the pile of dirt in PR to the holes in PG. And let's take a look at how to find the best plan among them. The first transport plan can be expressed as a joint distribution of I and J, with marginals PR and PG as follows. The amount of dirt that needs to be moved from bin I to bin J is the matrix gamma. The second possible plan can be made as follows. This is another matrix gamma. The more bins you have, the more possible plans you have. And we have a distance matrix D like this. This can be measured by the absolute values of I minus J. Let's notate the matrix gamma like this. And let's express the marginal probabilities PR and PG like this. The distance matrix is also expressed like this. The set of matrices gamma is pi. Then we vectorize the matrices gamma and D like this. As we saw in the previous video, Wasserstein 1 distance is defined as follows. The Wasserstein 1 distance is the smallest gamma-weighted average distance among those computed using all gammas in the set pi. This can be expressed as the sum of element-wise products between the optimal gamma matrix and the distance matrix. Since this is an optimization problem, the above expression can be written as follows. The gamma-weighted average distance for the simple example on the left can be written as follows. And the minimum of this expression is the Wasserstein distance. And the constraints are as follows. The sum of each column in the matrix gamma must be the distribution of PR. And the sum of each row must be the distribution of PG. This is a typical linear programming problem. This can be expressed in the standard form of linear programming as follows. The decision variable x is a vector of gammas that we are trying to find. C is the distance vector. And B is a vector consisting of marginal probabilities PR and PG. The matrix A can be defined as follows. This is the linear programming problem to find the optimal gammas of the Wasserstein distance. However, we are not trying to solve this LP problem directly. That is, our goal is not to solve this LP problem to find the optimal gamma and obtain the exact Wasserstein distance. Instead, our actual goal is to train a GAN model using this LP so that the Wasserstein distance is as small as possible. The primal form of the LP problem we looked at on the previous page is as follows. And the dual form for this problem can be expressed as follows. In this form, y is a vector of decision variables, and c is the distance vector. The constraints of the dual form are as follows. Now let's assume that the solution y star of this dual form is as follows. Then the maximum value of the objective function z tilde star can be written as follows. And using the notation below, z tilde star can be expressed as follows. Since PR and PG are probability distributions, this can be expressed like this, using the expected values. The x in the first term comes from PR, and the y in the second term comes from PG. The functions f of x and g of y are the optimal solutions to this dual form. But we are not trying to find the functions f and g. Instead, we replace the functions f and g with a neural network called critic, and then train this network to try to make z star as large as possible. Additionally, the constraints of the dual form should also be applied to the neural network. To do this, let's analyze the constraints. The constraints can be written as follows. Then the constraints can be expressed as a single inequality as follows. This inequality holds for all I and j. That is, this constraint can be expressed as follows. This tells us that for all I and j, f plus g must be bounded to the distance between I and j. Here, d is a distance, so it's a non-negative value. And in the distance matrix, all diagonal elements are 0. Therefore, the closer the numbers are to the diagonal of the gamma matrix, the smaller the transport cost will be. That is, when I is equal to j, d is 0. Therefore, this inequality holds when I is equal to j. And the point or region where this equation holds true exists within the feasible region. This is a stronger constraint than any other. We would like to apply this strong constraint to our neural network. Then the above z star can be written as follows. And the above inequality can be written like this. This is the constraint we will apply to our neural network f. This means that the difference between the outputs f of xi and f of yj of the neural network should not be too large. That is, the neural network f should have a smooth output without any abrupt changes for any input. We need to train a neural network f that satisfies this condition to make z star as large as possible. This is the basic concept of the Wasserstein GAN network. Next, let's look at the objective functions for WGAN training. As we saw on the previous page, the optimal solution to the dual problem for finding the Wasserstein 1 distance is as follows. Using this, the Wasserstein 1 distance can be expressed as follows. This is the original definition of the Wasserstein 1 distance. The definition by the Kantorovich-Rubinstein duality is as follows. infimum changes to supremum, and PR and PG are broken down into two parts. And additionally, we have a constraint like this. This is the constraint in this dual solution. This implies the one Lipschitz condition. If a function f satisfies the following inequality, the function f is called a one Lipschitz function. This means that the slope of the function f is less than or equal to 1 over the entire interval. That is, when a function f changes smoothly without changing too quickly like this, the function f is called a Lipschitz function. For example, the function sine x is a Lipschitz function, but the exponential function is not a Lipschitz function. Now let's use this to create the objective function of WGAN. The objective function of standard GANs is as follows. The objective function of WGAN can be expressed as follows. GAN uses this formula to estimate the Wasserstein 1 distance between PR and PG. This expression comes from this expression. As mentioned before, f is not a function, but a neural network. To roughly apply the one Lipschitz condition to this expression, the authors of the WGAN paper used a method that limits the size of the network parameter W to be between -c and +c. C is a hyperparameter, which is the clipping parameter. If W is small, the output of this network for any arbitrary input x will be small. And the absolute difference between the network outputs for two inputs x1 and x2 will also be small. Therefore, this approximately satisfies the one Lipschitz constraint. This expression can be written as follows. Replace sampling y form PG with sampling z from PZ, and replace y with g of z. The reason why this can be written this way has already been covered in the standard GAN. Here G stands for generator. Now let's denote f of x by the critic network d of x. This is a critic network, but we will denote it as D in the standard GAN notation and call it the discriminator. Then this expression can be written as follows. We estimate the Wasserstein 1 distance using a discriminator. The discriminator in a standard GAN acts as a classifier, whereas the discriminator in a WGAN acts as a regressor. The objective function for training WGAN can be written as follows. The discriminator is trained to estimate the Wasserstein 1 distance, and the generator is trained to minimize the distance. That is, the Wasserstein 1 distance between the PR and PG is shortened by the generator. Then PG becomes similar to PR. WG and WD are the parameters of the generator and discriminator, respectively. WD is updated by gradient ascent like this. And WG is updated by gradient descent like this. When updating WG, only the gradient of the second term is used since the first term is independent of WG. Next, let's look at the WGAN algorithm presented in the paper. First, we update the discriminator multiple times. We use this formula to update WD by gradient ascent. This is to enforce one Lipschitz constraint. WGAN clips the weights of WD to lie within a compact space from -c to +c. C is the clipping parameter. Next, we update the generator once. We use this formula to update WG by gradient descent. Theta is WG. This process is repeated until WGAN converges. Now let's implement a WGAN model in code. This code is very similar to what we used before. Let's just look at the parts that have changed from before. In the WGAN custom model, the loss function of the discriminator has been changed as follows. This is to find the Wasserstein 1 distance. Clipping the weights is handled separately later. And the loss function of the generator has been changed as follows. This is to minimize the Wasserstein 1 distance. Update the discriminator 5 times. We clip the weights to enforce 1 Lipschitz constraint. And update the generator. The rest of the code is identical to the previous code. Let's take a look at the results. The loss history of the discriminator measured during training is as follows. After 1,000 iterations, the loss converges to almost 0. D-loss is an estimate of the Wasserstein 1 distance. During training, this distance was estimated as negative. In principle, the Wasserstein distance cannot be negative, because distance metrics cannot be negative. However, since we use a neural network to roughly estimate this distance, we may end up with negative values like this. The loss history of the generator measured during training is as follows. After 1,000 iterations, the loss converges to about 0.05. After 100 epochs, the distribution of fake data is as follows. The red dots are fake data G of Z generated by the generator, and the blue dots are real data X. After 200 epochs, the distribution of fake data is as follows. The fake data is now a little closer to the real data. After 300 iterations, the fake data became slightly more similar to the real data. After 900 repetitions, the fake data became very similar to the real data. We can see that no mode collapse or mode hopping occurs. Let's run this code. The results are as follows. So far, we have looked at Wasserstein GAN. In the next video, we'll look at the WGAN GP model.